Okay. So welcome also from my side. I was explicitly asked to present on how to program with this high bandwidth memory called MCDRAM. We have seen the basics and the introduction from the hardware side, from the architectural side, and I will now present how that embeds into the operating system, Linux in that case, and how you can actually access the capabilities of the high bandwidth memory. And for this, we have a slide terminology or an introduction on terminology for these MCDRAM modes. We have heard about clustering modes earlier on. We also have these memory modes like cache or flat mode, and we will look into this. And then I will go a little bit deeper into the cache mode usage and the flat mode usage. And Tim already confirmed that you can have both modes available on the KNL cluster here available. And then I will also go into the specifics on how to use the flat mode, which is the explicit mode to utilize the high bandwidth memory from an application point of view, and how you can do this from a C program or from a Fortran program perspective. And for that, I think we can skip over the KNL architecture overview. We've seen that slide in the previous presentation and jump right into the integrated on-package memory. And you can see there are essentially three modes, whereas the last mode is kind of a mixture of the cache mode and the flat model. So it's called hybrid, but it's more, I would say, exotic to use. I haven't used it on my own, but we will focus on the cache mode and the flat mode. And once you understand these two modes, you can easily guess what the hybrid mixture of both of these is. And you can see in the visualization, there is essentially a way to map the entire DRAM domain into this MCDRAM memory, and to essentially have a direct mapped memory side cache. And every memory access would end up or be cached by the MCDRAM. And the flat model exposes both memory domains separately. It's a little bit odd. I think it's for the first time that you get NUMA domains that have no process. One of the NUMA domains have no processor or cores in it, right? This is a little bit special. Normally, if you have a dual or quad socket system, you have maybe two NUMA domains, and they correspond to each of the sockets. And both of the domains contain memory as well as cores. Actually, the memory that is attached to one of the sockets, and then the other domain with the memory attached to the other socket. Here, you have something special. You only have one socket, but maybe two domains, and one domain is kind of empty in terms of number of cores, and the other domain contains all the cores. And then if you visualize use the normal operating system mechanism to show the content of the NUMA domains, like NUMA control, -- hardware, or capital H, you can see also the traveling distances in terms of what the default memory allocation domain will be. We will have a look at this later on. Let's go into the cache mode usage first, and also into the advantages of the cache mode, but basically look into what it actually means to have a memory side cache. First of all, I will have on the next slide, I will have a primer on what caching and essentially associativity is about, so to remind you on what the terminology is on that slide, but you can always or already remind that the cache size on a normal CPU core is usually very small, right? It's a very precious resource, and it's a valuable resource on CPUs as well as on GPUs, and there's usually very little cache memory available. And the caching organization is, as I said, between these two kind of caches. It's typically on the CPU core, you have an n-way set associative cache, whereas on the MCD or the memory side cache, when you use the MCDRAM as a cache, you have a direct mapped cache. I will go into explanation what that is. And also the place where this applies is basically the cache inside of a CPU core is obviously very close to the core itself. It's right in there. But here, with this kind of a memory side cache, you have it more associated to the memory controllers. And as a primer for what caching means, and it's actually important to understand this, we have, as a mathematician, I would say there is no difference between all of these three categories because they are essentially all set as associative caches. You have basically a zero-way associative cache, which is direct mapped, and then you have an n-way or a fixed small n. And you can see the direct map cache is the simplest form of a cache. You can a hit would be you can hit the location in the cache just by knowing the address where it came from. You have a direct one-to-one relationship between those, and it's a very simple mathematic function you can think of that calculates the address in the cache. You say you have a certain memory address and you do some mod operation. You have say you have a cache line of 64 byte size. You will have you will split up the 16 gigabytes into 64 byte chunks, and then you will essentially have so and so many chunks, and you will use that as a modulus. You will do a division essentially for the hardware address, and then you will get the actual location in the cache. And this is a very simple operation. Each incoming address has a correct or one and only one single location where it can be reside in the cache. On the other hand, the disadvantage of the direct map cache is you also have conflicts, right? If you have a more DDR memory than cache, which is typically the case, you have 16 gigabyte of cache, but maybe typically on KNL, most people or most systems are equipped with 96 gigabyte of DDR4. You can fit in up to 384, but I think more usual is 96. Obviously, you will have some oversubscription for the number of slots that you can end up with in the cache, right? Obviously, you have 96 gigabyte versus 16, and somehow you have to map that into, and that obviously creates some conflicts, right? Although the granularity of the cache is in number of cache lines, not just in bytes, right? But anyhow, you will have some conflicts, and we will look into this and how to handle this later on. There are other explanations on fully associative caches and n-way associative, and they are basically hybrids or extreme cases of associativity. You essentially some of the caches, you will chop it up into buckets essentially, and you will have a mapping or a modulus function that maps you into a bucket, but within the bucket you would have the need for a full search in order to find the hit in the cache. So the direct map cache is essentially a single bucket version of it, right? You map into a single bucket, and then you have n buckets. So, I misspelled that. Sorry. You have a direct association between memory addresses and cache mapping. So the advantage of the cache mode is you don't need to do any source code transformations or changes for your application, because you don't care essentially about high bandwidth memory. You just execute normally, and if you use NUMA control -- hardware, you would only see a single domain. It's a very simple way to expose the entire hardware. You only have one domain, and it is full of cores, and it is a single domain in terms of the memory. And you can't do anything to bypass the cache. But on the other hand, you may have some reuse, right? If your application has some reusable part of the memory, you can obviously utilize that and make use of the cache to some extent, right? If you have a streaming application that entirely just touches all the memory one time, you only have overhead because of that model, because you maintain a cache for nothing, right? We'll see this. The benefit of the cache mode is essentially you can deal with legacy code as is. You just run it normally. Drawbacks are there is less available bandwidth compared to the flat mode. You only get 3/4 because of maintaining this memory side cache, and every miss on the cache induces a higher latency, because you first look into the cache only to find that there is no data in, and then you essentially trigger the transfer from DDR4 memory. As a reminder here, if you run the stream benchmark, you obviously see some overemphasized disadvantage of cache mode. Don't think this is true, right? The stream benchmark is made to stream memory. It is by design, there is no reuse of any data, right? So therefore, you only measure a disadvantage of cache mode, which might not be there if it is a real application. If your application has some reusable part, it can be beneficial to have the cache mode. And there are other implications that come from the cache mode. So for instance, since it's a memory side cache that you can't bypass, some of the architectural things that you have in the instruction set, like streaming stores or called non-temporal stores, they cannot bypass that cache. So they have a just overhead again. The streaming stores have no advantage in the cache mode. Basically, and you can also instruct the compiler to not generate these streaming stores at all. Normally, the Intel compiler and maybe other compilers, they have heuristics. If they see a loop with just a certain store instruction and they think that you will never touch that same array where you write into, they may generate streaming stores because it is just like touch and go, essentially. And it doesn't need to end up in any cache hierarchy. But this is not possible with cache mode. You always have to go through. There is another implication of this direct mapped cache. You have also some fragmentation that depends on the access pattern that the application uses in terms of memory allocation and run and use of memory. And it's more of an embedding. It's not an architectural disadvantage completely, but it's more like the way it is embedded and exposed with the operating system. And there are certain things you can do about this. And I think most sites or high-performance computing centers, they have some, or probably Cray does implement this in the batch or in the job scheduler. They just run some of these scripting before launching a job to make this, to essentially defragment the cache memory to some extent. We will look into some of the measurements. There are certain problems associated with this direct mapped cache. So for instance, you can have a degraded performance over time, or it looks at least like this. It looks like if you run the same application 2 days, 4 days later, and a lot of your colleagues scratched on the system and did something else before you, or just run the same application, because of memory usage and access pattern and allocation and deallocation, the performance looks degraded, and you can measure that. For instance, with the stream triad benchmark, you can see this on the top. This is the application we run here is stream triad, and you can see how the performance degraded. On the x-axis, you could say day after or the number of days that the system is up, but it is essentially something else, right? It is we run as an experiment a mix procedure, which is the same application with different workloads or different applications. And then you can see this, and you can resurrect from that deficiency. You can essentially put something into the job launcher and essentially defragment some of the operating system structures in the Linux kernel to get rid of this, degradation and performance. And the part or the tool or the script that does that is called the Zonesort. I will think that it is mentioned on the next slide. This is a very detailed insight, right? You can look at this later on and what the measurements are. But the important message here is the vendor or the compute center probably put something in place like Zonesort that helps you to resurrect from that problem, which is associated to the cache mode. Here is another application showing the same pattern, right? This is HPCG. Similar to stream benchmark, and you can see degraded performance over time or after running a mix of access patterns here. Anyhow, so there is a Zonesort workaround proposed, and I think it's upstream partly, or it is part of some curious package that we call XPPSL, which is like the many-core platform software stack follow-on that you perhaps know from the KNC timeframe. And it introduced some script in the 1.4 release that gets rid of this problem. And triggering the Zonesort restores the initial performance. You can also measure that and see that you can resurrect from that problem. Anyhow, I don't want to talk about problems, but more on the usage side. So you can also go for the flat mode usage, where you have absolute control, where you can place some of your arrays or data allocations in the fast memory explicitly, right? And usual or good candidates are all arrays that are contiguously accessed with, where latency is not the main bottleneck, but when you essentially have something that demands bandwidth, then you might allocate, say, all the large arrays that contain data or operands for your hopefully heavy instructions or heavy math, that they can be allocated in the flat mode or the high bandwidth memory explicitly. So accessing the MCDRAM in flat mode works like doing some there are POSIX extensions to the memory allocation, or you can just use libnuma on the Linux operating system that allow you to place the memory allocation in a particular NUMA domain. This is nothing new that always existed. You could do this prior to KNL. With multi-socket systems, you could essentially allocate memory on one of the two socket domains if you wanted to do that. It was possible. But now there is a good package that made that more convenient, and essentially it's called Memkind. It is a library that you can see also on GitHub, which essentially packages this together with some fast memory allocator, which is hopefully good enough and good for HPC applications as well. It also brings something that helps you with scalable memory allocations, like when you allocate memory in threaded regions and things like this. It might be just under one hood packaged, and you can just use and operate with that normally from C and C++ applications. Instead of using malloc and free, you would just use these kind of hbwmalloc and hbw free functions. And of course, you can LD preload and replace it entirely, and there are certain heuristics that you can also utilize. So for instance, there is a heuristic to LD preload the Memkind library and to let all the memory allocations that are larger than, say, a threshold go into the MCDRAM, just as a good heuristic that everything that is large is potentially also bandwidth demanding, and then it is a good idea to place it in MCDRAM. And yeah, that is basically the way it works. But there is more. There is more you can do when you actually run your job or have your job script on the KNL system. You can also go for the operating system primitive, the NUMA control. You might have used that for multi-socket system when you requested interleaved pages to overcome some NUMA issues. You can use that here as well in order to let the entire application run from MCDRAM. That obviously requires a mechanism or help in case the application doesn't fit into 16 gigabyte. You need to have a strategy what happens in that case, and we will see that on one of the next slides, I think. But here you can see how the Memkind library accesses the MCDRAM. As I said, you have something called malloc normally, but you would replace it by hbwmalloc. On the Fortran side, you don't have a standard library-based approach, but you have built-in or intrinsic functions built into the language, allocate and deallocate, and you obviously have to essentially communicate how to place that, or how to distinct between these kind of different allocations. And you can do this using directives in Fortran, and you can attach attributes to, say, certain array allocations. We will look into more details on an upcoming slide. Going for and it uses for the Intel Fortran compiler, it uses the Memkind library as well. So if you just use these FASTMEM attribute, you will link against the Memkind library that comes with the compiler, and then you will just under the hood also use the hbwmalloc. It's the same thing, except the mechanism is different to tell the compiler language-wise. I think this is more like an exercise or something to look at later on. The Memkind architecture, it is just on GitHub. You can look and contribute yourself or read the man page for it. You can just type man Memkind and then see some explanations for the API and also how it evolved over time. So we gave feedback, external people and other people gave feedback on what they want from this kind of library and how to proceed with this. And I think that went into, so there are things meanwhile for For instance, for the Fortran side, you have a module for Fortran which wasn't there in the earlier version, and other things that you can control. And there is also some standardization approach ongoing for the POSIX function that have not this kind of HBW prefix in front to just standardize the whole idea of dealing with different kinds of memory, fast memory or non-fast memory. Anyhow, so there are, similar to the reallocation, the allocation, and the query functions to ask for the size of a buffer, they are just similar for the Memkind API, similar to glibc or something else. There are also standard mechanisms for accessing the MCDRAM. So you just prepend for the execution of the program, you would just say NUMA control, some parameter, and then you name the executable of your application, and then the application parameters to execute with, or the workload. And you can see basically two of those in red. You can see the membind, and then you can name a node, which is typically 1. That means if you have a system that exposes flat mode with, quadrant or some all-to-all, you would just see two memory domains. Domain 0, which is the DDR4 RAM domain. You can see it's 96 gigabyte typically. If you look with Memkind, NUMA control -H, you would see there are two NUMA domains listed in the table, one with 96 gigabyte and another one with 16. And then you would just run the entire application by saying membind equals 1, then it runs entirely out of this MCDRAM. It is a good mechanism. Basically, it also doesn't require any source code change, right? You would just recompile, or you would just compile and run your application normally, except that you execute it with the NUMA control helper or utility. And then there is also a deviation, slight deviation. It's basically the strategy on how to deal with out-of-memory situations. You can also tell the NUMA control utility to fall back into DDR4 once you are out of out of MCDRAM, right? If your application eats up more than 16 gigabytes, what happens? You could, of course, it could terminate with some exception or error, but if you tell NUMA control -- preferred, you would just fall into the DDR4 RAM, right? You eat up all the 16 gigabytes, and then the rest of your allocations end up in the DDR4, which is reasonable, I would say. And sorry, this is just the wrong direction. NUMA control appears to make the flat memory mode almost as convenient as the cache memory mode. However, you should keep in mind, despite of this membind and preferred policy, there is a little bit a lack of control. What happens in the OOM situation, which is out of memory situation. And in particular, if you have an MPI application, which you probably have, it may lead to some of cumbersome effects, like if you have an application that eats more than 16 gigabytes, and your first rank is happy enough to grab all the 16 gigabytes, all the other ranks end up with DDR4 RAM, and then you have an unbalanced execution, right? One of your ranks is blazingly fast and high bandwidth, and the other ranks are just slow and sluggish. They run out of DDR4. This is something to keep in mind, and probably that's also easy to fix. You could use tools that essentially pre-chunk the 16 gigabytes and make the MPI run aware of a fixed slower or lower limit, essentially lower limit than 16 gigabytes. But just wanted to make you aware that this is not, the biggest and nicest invention. You probably have some need to control either at application level or to think about what happens with demanding applications that consume more than 16 gigabytes. There is one topic left, I think. That's probably interesting to all of you. I think most of you or some of you will program in C, C++, but there is some coverage for the Fortran side, and how to deal with dynamic memory in Fortran is, it's not a new topic. It's unlike C, you have a built-in a malloc type API, or you don't have a malloc type API. You have built-in intrinsics like allocate and deallocate, and then you would just need to essentially use this FASTMEM attribute, and you can make a list of arrays that are listed there for placement within the MCDRAM. That is basically a very simplistic way to deal with this. But obviously, there are always cases that are going beyond simple cases. First of all, I will look at this on the next slide, but some other interesting thing is the Fortran 2003 standard requires that the allocatable variables are automatically be deallocated when they go out of scope. Just as a reminder, that is like more like a automatic memory management behind since 2003. But anyhow, let's look at the FASTMEM status within Fortran, because you have some more varieties than just simple allocatable arrays. You sometimes have, for legacy reasons, pointers that are not attributed as allocatable, but actually attributed as pointers, right? And then you need to deal differently with this FASTMEM attribute. You cannot use the FASTMEM attribute in front of this and tell the FASTMEM attribute that array is something that ends up in MCDRAM. So why is that? Because the pointer in Fortran and everywhere else in any other language can point to anything you want. You can change that during the program flow. You can make array pointing to a different array. And obviously, it makes no sense to mark a pointer by itself as something that is in the MCDRAM. There is no reason that you can not change that, right? You can make the pointer pointing to something else. So it is something needed. And obviously, you can make a little bit helper. You can have an attribute or an array which is attributed as allocatable, and then you can make the pointer pointing to that. And then you are done, essentially. This is not a big deal, I think. And there are more things like this for the components of derived types where you have to deal with some of these workarounds. This is work in progress, and also feedback or basically feedback is needed, because it could be something that ends up in the Fortran standard. And if you are not if you don't feel well with the proposed solution, you can impact and make some impact on it, right? You can give feedback on it. For instance, we gave feedback on how to deal with components of derived types. So there's already some curious intrinsic like movealloc, where you can just use that solution that I proposed earlier, that you have an array which is the proxy array attributed as fast memory, and then you essentially you essentially let you essentially utilize the proxy, which is in the, and you can use it together with the movealloc intrinsic. There is something else you can do. The pointer attribute is also explicitly available with the hbwmalloc module. I think it's a colleague of our team who wrote it initially and contributed it to the Memkind library. But let me pick up the question here. There is one question.
Yes, sorry. Can you go back one slide?
Yes, sure. One slide back.
So it looks like you have to put the attribute just after the allocate, but not cool. So I was expecting to put the attribute actually just before the allocate. And not
yeah, this is one of the things that we propose. A while ago, we did some suggestions on how to improve the way the FASTMEM attribute is incorporated with the Fortran compiler, and we made suggestions on, I think this is actually one slide or two slides later, where we also wanted to have it working together with the allocate intrinsic by itself, right? To tell essentially the allocate function that is an allocation that should end up in MCDRAM, right? It's more natural. Here it is associated to the declaration of the variable, whereas allocate is the actual allocation, but this is not, right? This is very good feedback, and it's a very obvious feedback, and we already told them to do so, right? I will show that. I was on this slide about Fortran FASTMEM status, and I think there is more about Fortran and dynamic memory, and you can see exactly what you asked, basically. We also want them to have the intrinsic allocate, or the allocate intrinsic be used for dynamic memory allocation, and we want to have the attribute in front of the allocation, right? This is exactly here the case. we want to have some way to express it together with the allocate intrinsic. Okay. Oh, sorry, I just, yeah. Flat mode usage in Fortran. Yeah, this is back. Sorry, it is. Yeah, so more recapitulation on the hbwmalloc module, where you can just deal with high bandwidth memory in a C-style manner, but there are obviously disadvantages. It comes close to essentially tuning the allocate, deallocate intrinsic, but it is more like C, but rather unnatural for Fortran, right? You can do hbwmalloc within Fortran by itself, but you then have some inconvenience. They simply did some ISO-C binding for the hbw or Memkind library, and then you have to declare your pointers like type C pointer, and then you call hbwmalloc on it, which is, you know, not ideal, I think, but it works somehow. So here you can see an example on how to do that. This is more like C. You have some variable and you do some hbwmalloc on it, and then you also have to call hbw3, which is again inconvenient, right? You have to have match between deallocation and allocation. Of course, you cannot use the deallocate attribute because you explicitly use some other functionality for it. There is some progress made for Fortran's FASTMEM future, and you can probably, here is actually the slide that I mentioned earlier. A solution would be to have the directive in front of the allocate, which gets rid of the thing. Maybe they implemented, or maybe they have implemented that. There's another question?
Yeah, I just have a question. I guess it's a feedback
okay.
about these directives. So to me it seems, if you think about memory hierarchy or memory architecture moving forward, you're going to have a more complicated hierarchy. Okay. You might have some on-package memory like MCDRAM, DDR, you might have some non-volatile memory, some else slow. And it seems a bit strange to use a word like FASTMEM, because like, what does it really mean, FASTMEM? Yep. We've already said that the MCDRAM has actually got worse latency, so some might argue that it's slower memory, it's just high bandwidth memory. So perhaps the standards committee need to think about how they're going to, what they're going to call these directives a bit more carefully.
Yeah, perhaps we will hear something about it from Michael Clem. What is ongoing in the OpenMP with respect to these kind of memory hybrids. This is exactly right. You know, we have more than FASTMEM, and we know it already, right? We will have non-volatile memory, and we already know that we need to express certain things, and this is not an easy task. But the good thing with the directive here is you can easily retire that as a kind of a legacy and a first shot. And we will see if we get something better in our second try. But we have to wait and see what the standardization gives us with OpenMP, and I think we will hear on that later on. So Michael already says or confirms. With that, I think I'm generally open to questions. If you have some questions regarding the FASTMEM, but I think it's pretty easy and straightforward to use. It's either cache, or you can do the dump solution like NUMA control, or you can go for the ninja way by putting some FASTMEM attribute or some explicit kind of allocations inside of your application. These three options are essentially there, and they all sound reasonable, I think. Okay.